Solar flares. A solar flare is an intense, localized eruption of electromagnetic radiation in the sun's atmosphere. Flares occur in active regions and are often, but not always, accompanied by coronal mass ejections, solar particle events, and other solar phenomena. The occurrence of solar flares varies with the 11-year solar cycle. Solar flares are thought to occur when stored magnetic energy in the sun's atmosphere accelerates charged particles in the surrounding plasma. This results in the emission of electromagnetic radiation across the electromagnetic spectrum. Solar flares affect all layers of the solar atmosphere, including its photosphere, chromosphere, and corona. The plasma medium is heated to tens of millions of degrees Kelvin, while electrons, protons, and heavier ions are accelerated to near the speed of light. Flares produce electromagnetic radiation across the electromagnetic spectrum at all wavelengths, from radio waves to gamma rays. Most of the energy is spread over frequencies outside the visual range. The majority of the flares are not visible to the naked eye and must be observed with special instruments. Flares occur in active regions, often around sunspots, where intense magnetic fields penetrate the photosphere to link the corona to the solar interior. Flares are powered by the sudden release of magnetic energy stored in the corona. The same energy releases may produce coronal mass ejections, or CMEs for short, although the relationship between CMEs and flares is not well understood. The frequency of occurrence of solar flares varies with the 11-year solar cycle. It can range from several per day during the solar maximum to less than one every week during solar minimum. Additionally, more powerful flares are less frequent than weaker ones. For example, X10 class, or severe, flares occur on average about 8 times per cycle, whereas M1 class, or minor flares, occur on average about 2,000 times per cycle. The duration of a solar flare depends heavily on the wavelength of the electromagnetic radiation used in its calculation. This is due to different wavelengths being emitted through different processes and at different heights in the sun's atmosphere. After the eruption of a solar flare, post-eruption loops made up of hot plasma begin to form across the neutral line separating regions of opposite magnetic polarity near the flare's source. These loops extend from the photosphere up to the corona and form along the neutral line at increasingly greater distances from the source as time progresses. The existence of these hot loops is thought to be continued by prolonged heating present after the eruption and during the flare's decay stage. Much is yet to be discovered in concerning solar flares, but what is definite is our concern and importance in monitoring such magnetic energy bursts. Be sure to subscribe for more Space Rewind and tell us in the comments what you would like to see next in an upcoming video.